Hello everybody, good afternoon and welcome to today's class. Today we will explore the topic 3.3, which is energy. The way in which we're going to do this is in four sections. First, we're going to talk a little bit about what energy is as an intro. Then we will talk about kinetic energy. Then we will talk about something called potential energy. And finally, we will talk about something that is called total mechanical energy. Today, we will be looking at the first two of these subtopics. So let's begin. So what is energy? Energy is defined as the following. Energy is the capacity to do work. It's a very simple definition, and I'm going to try to exemplify this definition in two ways. The first example that I'm going to explain is the following. Let's suppose that you have a surface and there's an elevation here and more surface. Okay, so let's suppose that we have attached to this little elevation, we have a spring, un resorte. And this spring is completely relaxed. It is neither compressed nor elongated. Okay, it is completely relaxed. And let's suppose that over this surface there is a box coming from the left towards the right with some velocity. And let's also suppose, for the sake of the argument, that there is no friction at all between the surface and the box. There is no friction. So the box will approach the spring, and sometime later it will hit the spring, right? So what's going to happen to the spring once the box hits it? Well, as you may imagine, the spring will compress completely. Okay? So let's analyze these two situations. We say in the first time lapse, which is this one, we say that this box has energy. And we say this because by virtue of its motion, this box can do work on something else. In this example, the box will do work on the spring. But remember, what is work? Work is basically applying a force on something, and that something being displaced a quantity x. Now you must remember that we also have in here another factor, which is the cosine of the angle between the force and the displacement. But if in the case of the force and the displacement being parallel, you must remember that the angle was 0 and that the cosine of that angle was always equal to 1. So when the force and the displacement are parallel, we can actually erase this little part because this will be 1. So for simplicity, we will get away with this. Let's continue. So the box will do work on the spring, and therefore, as a consequence, the spring will compress. Now, at this other time lapse, what we say is that the energy contained in the box is completely gone now, because now the box is completely at rest. And now we say that the energy of the spring, we say that the spring has energy because it's now compressed. As you may know, when a spring is compressed, it can decompress and do work or apply a force on something else. In this case, if we let go another time lapse, what's going to happen is that the spring will decompress again, right? And all the energy contained in the spring at this point will be one more time given away to the box. So the box now will be moving in this direction, and one more time we say that the box has energy because it's moving. And now the energy of the spring is one more time 0. Okay, so this is an example of conversion of mechanical energy, which the box has, into something called potential energy of the spring. I will give you another example. Example number 2. Let's suppose you have a balloon on a surface, and you have a little coin on top of this balloon. Okay, now this is one time lapse. Now, what will happen if you come up with a lighter and you hit the balloon? I don't know if you knew this, but when you hit a balloon, the balloon inflates, and therefore, as a result of this heat, the balloon with the coin on top will raise. In other words, the fire or the heat that is coming out of the lighter will raise the coin a little distance with some force. Okay, so basically this energy, which in this case is heat energy, will do work on this coin, not specifically in the balloon. The balloon is just the mechanism by which this energy will perform work on this coin. How? By applying a force on the coin in order to raise it over a certain displacement. Okay? That is, the heat raised the coin from some height to a greater height. So basically, that's what energy is. Energy is just the ability to do work on a particle. Now let's talk about different types of energy. As you may have heard, there are many forms of energy. For example, mechanical energy, thermal energy, nuclear energy, chemical energy, and so on. And all of these are between themselves, you can convert one to the other. I'm going to give you another example of this type of conversion. For example, I don't know if you have experienced this. Suppose that you have your mixer. And you put some water in it. We have the blades in here. Usually there are 3 blades. And let's suppose that you turn on the blender, this blender. Okay, what's going to happen? So the blades are going to rotate extremely quick. And therefore, these blades, because they are rotating, they have something which we call mechanical energy. Okay, because they are rotating extremely fast. Now, that mechanical energy will be converted into thermal energy in the water. I dare you to perform this experiment on your own. Do this, leave the blender on for perhaps 2 or 3 minutes at its highest speed, and later you will notice that if you touch the water will have become much hotter. Okay, I don't know if you have experienced that. So that is a type of conversion of mechanical energy into thermal energy, and you can convert any of these types of energy into any other, something which we will see later. So now let's talk about what kinetic energy is. So let me first give you the definition. Let's suppose you have a particle. This particle has a mass m and it has a velocity v. So under this context, we define the kinetic energy represented by a k as the following. It's 1/2 times the mass of this particle times the velocity squared of such particle. So this is the definition of the kinetic energy of a particle. It's 1/2 times its mass times its velocity squared. And I want to tell you two little comments about this concept. The first one, it is that kinetic energy is measured in joules, just like work. Do you remember? Work is measured in joules. So that means that there is a connection between kinetic energy and work. And in fact, there is a connection between any energy, any type of energy, and work. And the second remark is that this energy, kinetic energy, is due to motion. When you have a particle moving, we say that it has kinetic energy. On the other hand, if you have something which is completely at rest, suppose that the velocity of this particle is 0, it doesn't matter how massive it is. Let's suppose it's 1000 kilograms. If I calculate the kinetic energy of this very big particle, and I mean very massive, we have to multiply 1/2 times its mass times its velocity squared, and when we substitute the quantities, we will get 0 in the end, 0 joules. So a particle that is not moving does not have kinetic energy. Okay, now let's talk about the relation between work and kinetic energy. Okay, there's a very important result in physics, one of the most important in mechanics, that says the following. When you have a particle and you do work on this particle, that is, if we apply a force over a certain displacement, what's going to happen is the following. That work will be equal to a change in the kinetic energy of the particle. Or, in other words, when a force does work on a particle, it's going to change the kinetic energy in this way. Remember that this triangle, what it means is some final quantity minus some initial quantity in here. Okay, so this is what we know as the work energy theorem. I know that I'm not demonstrating this theorem, at least not in this video, because it's a little long. So what I'm gonna do is, for those of you who are really interested in physics or mathematics, or those of you who want to go into engineering, or just those of you who really want to understand why this is the same as this, I will add another video as an appendix in which I'm gonna prove this theorem. Okay? But for those of you who may not be so much interested, just accept this as a fact.